Okay, so we meet for the next lecture of our Modern Dynamical Systems course. I think this lecture will be the last one among the regular lectures. And after the May holidays, we're going to meet only if some of our students would like to make the presentation. So the plan for today's lecture is the following. We start with a recall of famous Ratner's theorem that we studied last time. I hope the lecture was available, right? And then I tell you about two famous plots related to Ratner's theorem. The first thing is the application of Ratner's theorem, one of the most celebrated one, when dynamists helped people in number theory to solve a very long-standing open problem named Oppenheim conjecture. And the second thing is more related to this part that was about modular spaces, interval exchange transformations, and so on. Namely, I will show you what a famous theorem by Alex Eskin and Maria Mirzakhani, that is very often called the magic wand, what it states, and we will see that it's very similar with the idea of Ratner's theory. We will not prove anything, we will just discuss morally what's going on. And in the second half, Kirill Zernikov will present his talk about Birkhoff-Ergodic theorem. So let's start. So first, I start with a recall of the statements of Ratner's theorems. So the first guy we introduced previous time was Ratner's orbit closure theorem. And we had the following. We took an homogeneous space of finite volume, and it was a Lie group. That was a symmetry group of our homogeneous space, so we want that it also has a finite volume. And we took a connected subgroup of our Lie group G. Generated by unipotent elements. So we consider an orbit of U in X. And then the closure of this orbit is necessarily a homogeneous space of finite volume. And in particular, there exists an H, which is kind of intermediate group between U and G, such that the closure of the U orbit of X can be seen as an H orbit of X. This theorem was conjectured by Raghunathan, and basically it asserts that the orbit of any unipotent flow is dense in some homogeneous space of a finite volume. We will apply this theorem in Oppenheimer conjecture in a few minutes. Before I recall you to other theorems, because I will use it not directly, but as an example in the context of Eskin-Mirzakhani work. So the second theorem was Ratner's equidistribution theorem. we take X, G, U, H as before. There, as in the previous theorem. And we also assume that U is a one-parameter group what does it mean? It simply means that we consider it as the set of some homomorphisms T, GT. So then we can state much more than this. We can state that it's not just minimal, so dense inside of this closure, but it's also equidistributed. This was a conjecture by Dani, and we discussed at the previous lecture what does it mean exactly. I wrote you the formula, maybe we can repeat it, that for any continuous function, f hx to r, lim t goes to infinity, 1 over t f gtx dt is equal to hx, that's from 0 to t, of course. It's the same as the integration over the normalized Haar measure on hx. So this is the second theorem, and then there was the third one, which is also quite cool. I will also use it as an illustration for the ideas of Eskin and Mirzakhani. It's the measure classification theorem. So just wait a second. So we take a finite volume homogeneous space as before, and G is a connected Lie group, which is a symmetry group. And we consider a connected subgroup of G generated by unipotent elements. And we take a probability measure on X, which is ergodic under the action of our group. Then it's nothing else but a Haar measure for some smartly chosen H. for some h which is in between. So now let us talk briefly about how to get the Eskin-Mirzakhani theorem and what it is about. Actually, the proof is very complicated. But first, I want to state it, and I want to preserve these theorems written so that you can compare the statement. And then we'll comment a little bit on the proof, but it's very, very complicated. So let us forget for a moment what did we learn in homogeneous dynamics and go back to the Teichmüller one. You remember we lived in a world of modular spaces and SL2R action in these modular spaces. So I recall you the theorem that we proved, and it took a lot of efforts from our side actually. The one by Mazur and Veach. About the fact that the total volume of every stratum, you remember what stratum means, that we fixed the type of singularities for the surface with one form on it. So this is finite. And then we discussed that the group SL2R and its diagonal subgroup both act ergodically on every connected component of every stratum. And there is a theorem that we have not proved directly, but it's closely related to the things that we proved, actually. Because maybe you remember that we checked that almost all Keen's interval exchange transformations are uniquely ergodic. So a similar thing can be checked for translation surfaces. And it was done indeed by Mazur. And he stated the following thing, that he took a translation surface, and suppose that the flow in the vertical direction on S is not uniquely ergodic. It happens rarely, as we know. And then for any compact set K, so if we take a compact, in our modular space, in the ambient space of translation surfaces, the trajectory GTS of S would never visit K for T sufficiently large. So if you want, you consider the action on S of a diagonal subgroup given by Et E minus T, and it eventually leaves any compact set. And where does it go then? It goes to the multidimensional cusp of our modular spaces. So what does it mean? It means that the geometry of modular spaces is quite complicated because, okay, normally it's almost homogeneous, but there are some special parts such that if we enter this part, we will never go back. In some sense, it contradicts what we feel when we apply Poincaré recurrence theorem, right? Because typically there you go back to any subspace of positive measure. Indeed, it's also the case here, but it happens almost always. You remember it was the case in Poincaré theorem. We did not expect that all the points would go back. Also here, not everybody goes back, but those who are really exceptional because they correspond to non-uniquely ergodic situation, they escape to the cusp. And so it kind of forces us to ask ourselves how can look like the geometry of the corresponding modular space. If it's not an homogeneous space, then what it is. And we are ready to state the theorem by Alex Eskin and Mariam Merzakani. It will partly answer this question. I don't want to remove the statements of Ratner's theorem, so I need to look for a space to write it up somehow. Sorry for possible inconvenience. So that's what people who were very excited when it appeared, sometimes they call it magic wand theorem. So they say the following thing. And you will see how close it is morally to Ratner's ideas. So the closure of any GL2R orbit is a complex suborbifold. Possibly with self-intersections in period coordinates. I hope you remember what it was, the period coordinates. If you forgot, you just think that it was what we use as the sides of our polygon, the one that was used to construct the translation surface. So this vector. So in the period coordinates, in the corresponding space of translation surfaces. Locally, this orbifold looks as a affine subspace. So despite of having cusps, it's something that is relatively nice that we can study with some very basic instruments of algebraic geometry because it's a suborbifold. You know, there is a manifold, and then the next level of how perversive things can be, there's an orbifold, and this is a suborbifold, and locally you can see it as an affine subspace. And moreover, we can classify the measures, and any SL2R invariant measure is supported on a suborbifold and in this period coordinates, this suborbifold is nothing else as an affine subspace. And so this measure, the measure locally, it's just an affine measure. on this affine subspace. So you see that this result, in some sense, can be seen as the kind of extension of the Ratner's theorem to some non-homogeneous space, because we know that our space is not homogeneous. We just discussed that we have cusps. So it's not homogeneous, but in some sense, it's the best thing we could hope for. Indeed, it happened with us, because we get a precise classification of the measures, and it's pretty analogous with the things that we had in Ratner's case, right? Just the difference is that here we knew that it's a hard measure, and here we do have just an affine measure, but morally it's the same thing. And what is pretty important is this word any, because as you saw before, we can treat a lot of situations using just the result by Mazur-Veach and its further developments, like this Mazur criterion. But we are armless in the case when, for instance, we are given a particular translation surface and we want to say something smart in this situation. Because all our theorems only say what's going on when you have almost every, and then Mirzakhani and Eskin tell us what to do when we have to consider any situation. So I think that the first part is indeed by Mirzakhani and Eskin, and the second part about the measures, maybe it was proved also in collaboration with Mohammadi, another Iranian mathematician working in US. But it's not crucial. The key ideas, they came from this paper. And Maria Mirzakhani was awarded Fields Medal for the results that Sergei Konstantinovich explained some weeks ago on the counting of geodesics and this theorem, while Alex Eskin, he was already too old to get the Fields Medal, but he got the breakthrough prize for these results, $3 million. So it's a very celebrated theorem. In some sense, people expected something like that, and it was a conjecture by another very strong mathematician, very cool one, Kurt McMullen, who was a PhD advisor of Maria Mirzakhani. And Kurt was able to do these kind of things, but only for a very small stratum, for a stratum with two singularities. But in a full genericity, completely different tools were required. So now I want to show you, when you saw that, I hope I convinced you that it's a kind of, in some sense, an extension of Ratner's theorem, despite the fact that it required a lot of additional work. Already this is a very strong and cool result, but in order to get this one, you need to add a lot of more ingredients. In particular, they used the results in homogeneous dynamics by Benoit and Quint, but also they had to understand very well what's going on with the Lyapunov spectrum and study the related algebraic geometry and so on and so forth. So it's a kind of a mix of homogeneous dynamics, like Müller dynamics, and algebraic geometry. It all mixed, and that's what people had to add to this cocktail to get Eskin-Mirzakhani theorem. And so now I will illustrate briefly on a couple of examples. Why do people care about this theorem? What kind of problems it helps them to solve? And then we will go back to Ratner and apply it to the problem in number theorem. So applications. The first application is rather a physical one. Imagine that you have a room with mirrored walls. So you have mirrors on the walls, and your room is a kind of a polygon, and you want to illuminate it with a single lamp. And you ask yourself either the single lamp is enough or not. And there is a theorem that uses this cool result. It's a theorem due to Barak Weiss, Samuel Lelièvre, and Thierry Monteille. It states a very simple thing that for any translation surface, for any x, the set of points which are not illuminated by x is always finite. Another famous application of Mirzakhani-Eskin theorem is the wind tree study of wind tree model. By Vincent Delacroix, Pascal Lebert, and Samuel Lelièvre. So in this case, they studied the following billiard. You put rectangular obstacles on some fixed distance from each other, and you consider an infinite plane as a billiard table, and try to study what's going on with the trajectory of such a billiard you reflect from the sides of these obstacles. The motivation to study it comes from statistical mechanics. A wind tree model was introduced by Ehrenfest's wife and husband, who were trying to model some processes in statistical mechanics. And what these guys were able to do, they computed exactly the diffusion rate of the trajectory for such a billiard. And once again, it was using a lot the result by Eskin and Mirzakhani, because their idea was the following, that you can study now any translation surface. So they associated a translation surface with this model. You are gluing the parts that are connected by your trajectory, so you get a finite translation surface. And then you can apply some technique related to interval exchange transformations to connect the diffusion rate with the Lyapunov exponent of the corresponding cocycle of the Rossi reduction. And then once you do have all these ingredients, you apply this theorem and you compute the corresponding Lyapunov exponent precisely using some algebraic geometry, because you can understand what kind of orbifold you deal with and use the results of algebraic geometries. So people got a lot of smaller results using this great tool. And I hope that now it was a kind of a way to build a bridge between two parts that maybe looked very different to you, the one on homogeneous dynamics and the one in the Teichmüller dynamics. You see that apparently you may use tools from one thing to prove things about another one. And now it's a moment to introduce you to the applications of Ratner's theorems themselves, not their extension. And I will tell you about the most famous one, the Oppenheim conjecture and the Margulis contribution. Actually, Margulis did his work earlier than Ratner proved her theorems. But he had to make a kind of a particular case of what was later covered by her results. So in reality, now you can apply directly Ratner's theorem to get his observation more directly than he did it, and the ideas were very similar. So we will use it as an illustration for Ratner's orbit closure theorem, which is written here. The idea is the following thing, that Oppenheim conjecture concerns the possible value of quadratic forms in more than one variable when all the variables are restricted to be integers. So we consider a quadratic form. we have more than 2 variables, or at least 2. And all the variables are integers. And we are interested what kind of numbers we can get as the values of these forms. So very famous illustration of this kind of question is a famous 4-square theorem. It's not by Margulis, it's much simpler. It's already by Lagrange. So it asserts that the set of possible values of a quadratic form, which is a sum of 4 squares. So it tells you that you can get all the natural numbers. So you can get 1, 2, 0, 0, 1, 2, etc. So all the numbers you can obtain at the values of this form. More generally, if you take this quadratic form, any positive definite quadratic form, then say in m variables, possibly with irrational coefficients, and then you consider q of zm. It's a list of possible values. It's easy to see that it will be a discrete subset of positive real axes. So the fact that we will live in a positive real axis, it's easy because you have a positively defined quadratic form. So the hard part is to prove that it's discrete. But still, it's kind of a doable thing. And since today we discuss a lot the Fields medals, because also Margulis is a Fields medalist, so we will cite one more Fields medalist. It's Bargava. It's a joint theorem by Bargava and Hanke. So it's a positive defined quadratic form. Quadratic form. With integer coefficients. So then they represent all positive integers if it represents all positive integers up to 290. So if we were able to get all the numbers up to this number, then we will get all the numbers. Quite a funny theorem. So, okay, this is not the greatest result by Bargava, it's just funny. So, okay, we know what to do when it's positively defined, the quadratic form. And in this part, number theorists were good enough by themselves. They did not need to call a dynamist for help. Apparently, they found some issues at the moment when they wanted to switch from the positively defined forms to the indefinite ones. Okay, negatively defined, you treat similar. But what to do with indefinite ones? And at that moment, they had to call dynamists. because a number of things may happen. Let's see what exactly. For example, one option is the following, that let's see that Q, now it's indefinite. If it has integer coefficients, then I claim that it can take arbitrarily large positive or negative integer values. But at the same time, it can get gaps. And some gaps can be quite interesting. For instance, let us consider the case of two variables. For some d, which is integer. So you have to work a little bit with some class field theory of Q square root of d. So you work a bit with Galois. And then for the first time, people found the answers, what can happen here. And already Gauss was able to deal with this situation. Now, if you have commeasurable situations, so they are not necessarily integers, but they are integers multiplied by the same constant. So for instance, you multiply everything on square root of 2. And then it's not any more integers, but still they are commeasurable, then you can get a similar situation. But what happens if you don't have integers and the coefficients start to be incommensurable? In two variable case, we still may have some discreteness in the representation. For example, you can fix a number that corresponds to a gold ratio and consider Q n1 and 2 as n1 square minus phi n2 square. And you can check that it cannot get arbitrarily close to 0. Basically, the reason is that the golden ratio is very hard to approximate by rational numbers. So if you look at this form, you struggle to get as close to 0 as you want. However, once you increase the number of variables, you have a very different situation. And that's what Oppenheim treated in his conjecture. Finally, we are able to state it after such a long teaser. So Oppenheim in 1929 said that if you have an indefinite quadratic form, of 3 or more variables, and the coefficients are incommensurable, then there is no discreteness in the following sense. He claims that Q of Zm is dense in R. And somehow the harder case, the most difficult one, happens when you deal with the case of 3 variables. 3 variables are the most complicated. And it was resolved by Margulis in 1989. You see, it looks as a pure problem in number theory. So it's not obvious at all how the dynamics may help in this situation. But it may, and we will see in a moment how it will work. So we need to show that the image of that 3 under the quadratic form Q is dense in R, right? That's our task, according to Oppenheim. So every quadratic form comes with a special orthogonal group. SOQ. Defined as an orientation preserving linear transformations that preserve Q. Linear algebra tells us that it exists. So it's I will provide you a couple of simple examples. So for instance, if you are given x1 square plus x2 square plus x3 square, then you have SO3 in such a role. If you are given x1 square plus x2 square plus x3 square minus x4 square, you are given a Lorentz group. So there are examples. And the image of that 3 under Q is the same as the larger set SOQ, this 3. So if Q is indefinite, then we know that Q of R3 gives us the whole R. And so it is sufficient to show that this SOQ, the 3, is dense in R. Right? You understand that. It's because Q is indefinite. So for minor technical reasons, we will prefer to work with one component of this SOQ, the one that contains identity. So I will denote it by SOQ plus. So here, kind of an analogy with the Euclidean case can be useful. So we can spin around the lattice Z3 by a Euclidean orthogonal group SO3. And we trace out a union of spheres around the origin. And the radio of these spheres, they are precisely those numbers whose square can be expressed as the sum of 3 squares, right? So SOQ Z3, it's not dense, because not every number is a sum of 3 perfect numbers, right? So here, what do we say? Is that in case when the conditions of Oppenheim conjecture are satisfied, then you spin a lattice by an irrational Lorentz group, and we trace out a dense set. So we want to apply Rotner's orbit closure theorem. In order to do that, we have to see, to look at this SOQ plus Z3. We want to see it as an orbit of UX. We want to say that it's an orbit, right? Because we want to get the statement about the density. That's exactly what we had there. So we need to see it as an orbit of some point. And we want to do this. It's in some symmetric and some homogeneous space, G factor gamma. So obviously, there is a good candidate for U, because kind of, we don't need much of fantasy for it. But what to do with that 3? How to consider it? We want to turn it somehow to the point of the homogeneous space. The obvious idea everybody has is to take that 3 as a lattice, and so you consider it as a 0 coset in the tori you get when you consider a factor R3 Z3, right? But it doesn't work, however, because unfortunately you have this torus, but it's not a subgroup of R3, so we cannot force this person to act here. It doesn't want to act there. And so we need to lift up everything to a larger symmetric space, such that this G is a symmetry group that can accommodate this as a subgroup. You understand the issue, right? The most natural way how we could put it into the framework of homogeneous spaces didn't work because this was not a subgroup. It was too big. So we needed to construct another homogeneous space such that U can be considered as a connected subgroup of G. So we needed something else. The problem with that, this torus the modular spaces for translation of the lattice Z3, but this is not a group of the translations. So instead, what is it? It's a group of unimodular linear transformations. But then, what is the natural way to think about it? It's a subgroup of SL3R. So this group, we can say that we will consider it as a subgroup of SL3R. But SL3R is not that bad. It's also a Lie group. So we start to suspect that maybe we have to use it as a G and find some smart gamma. So this group acts on lattices. And what is the stabilizer of this action? Definitely, it's a lattice SL3Z, right? It's a stabilizer of the action of this group on Z3. So, but if you have this, what can you see? You can consider a factor, SL3R or SL3Z, and consider it as an X. It has some disadvantage. In particular, it is not compact, but still it has finite volume. It's good enough for Ratner. She never asked us to treat only compact case. She wanted to check that this X has a finite volume, right? And this is true in our case. So now this is our G, this is our gamma, this is our U acts on X, so we take SL3Z as an origin in this X, and the standard lattice is a 3. That 3 can be seen as, you can identify these two things, right? Here you put 3 integer numbers, and here you choose the same, so you can consider it like that. So now, if Ux is dense in X, then it implies that the set of matrices that would look as SOQ plus SL3Z, so it's dense in SL3R, right? That's what Ratner gave us. So if it's true, we cheated a bit because we have not checked anything about the unipotent elements up to now. But if we do have this density, then we can apply it to E1, to the first basis vector. And once we apply it, we conclude that actually SOQ plus Z3 is dense in R3 as required. This already Raghunathan understood. So we need to check that this is true, that Ux is dense in X. And here the moment to use Ratner's theorem, but let's check that we have everything for all the assertions. Assume that Ux is not dense in X. You remember this group. So assume it's not true, that this density statement doesn't hold. Then it must be much smaller. It must be contained in a closed finite volume orbit for some proper closed connected subgroup H, right? So to apply the theorem, we need only one ingredient. We need to check that unipotent statement is satisfied, right? Because everything else we checked. We know that we have Lie groups, finite volume, everything. But we don't know why do we deal with unipotent part. So this has to be checked. And we have to look at this Lie algebra of SL3R. And SOQ plus, it shows that the only candidate for this H is SOQ plus itself. And this is a moment where we apply a lot that we live in a three-dimensional space. It will not be true if you switch to any other dimension. And so SOQX is closed and finite volume. And in particular, you have that the intersection is a lattice in SOQ plus. So then the rest is quite simple because you apply the theorem and you get what you need. You need to be accurate to check all these things, to control that you have unipotent, that you have lattices, but this can be done by some general tools of group theory, Lie group theory. So this was a kind of illustration when a pure question in number theory can be restated in dynamical terms, and once we do that, we can apply such a powerful tool as Ratner theorem is. I think this is a moment to stop, actually, not only my presentation today, but in general this course. So if you want to give a talk, let me know. We will find a good plot for you. And if you want to know about something else or know more about these things, also let us know. But in general, we covered all the topics we wanted, and so we may make a short break, and then Kirill continues with his presentation.
Теперь он работает, да? Так. Сюда прицепим. Так. Okay. So hello everyone. Today I will prove the Birkhoff's ergodic theorem, which is widely regarded as the most important theorem in ergodic theory. So let's begin. But before we begin the proof, I'll actually give you a small reminder about the dominated convergence theorem and the monotone convergence theorem, because we are going to use them a lot. Just a quick one. So if we have a series of measurable functions that converges to some function f, and the fan is a series, and these functions fn are bounded by some integrable function g of x, then we can swap the symbol of limit and the symbol of integral like that. And yes, and we have the probability space x, s, with measure mu, and that's from the beginning, and this is the dominated convergence theorem, and the monotone convergence theorem states that if we have another series of functions, of measurable functions, that converges to some function f, but now we need convergence only almost everywhere, and the sequence of functions fn is increasing, so fn is less than f2, f2 is less or equal than f3, and so on. We can swap the symbols of limit and integral again, just like that. And I mean, I'm not going to write this one, it's just integral of s f d mu. Okay, so I'll leave it there because we are going to use them quite a lot. Now I'm going to state the main theorem. It's not the Birkhoff's ergodic theorem, but it's gonna follow shortly after we prove the main theorem. Okay, so let's so we have space x, mu some measure on that space. Let T from x to x be a measure preserving map, and the let f be some function, some real valued function on x, some real valued integrable function on s. Yeah, and also we have some Borel sigma algebra. Let's write it like that. So the first part is that there exists such a limit that we are going to call f tilde, such a function f tilde, and it looks like this. This limit exists almost everywhere. This is the first part. The second part is that this f tilde function is t invariant, and the last part is that for any t invariant subset A of our sigma algebra, the integral of f tilde is the same as the integral of function f. Okay, so this is the main theorem that we need to prove. But before we start the proof of the theorem, we will need a quick proposition. Proposition 1 if we have some integrable function on our space X, then the integral of ft d mu is the same as the integral of f d mu, and the function f is probably has to be t invariant, or maybe not. Okay, maybe not. Well, the proof is very simple. For simple functions, it's quite straightforward. Now assume that f is not simple and f is positive. Yeah, if f is positive and f is not simple, then there is some sequence of simple functions that converge to f. So we can write that integral of f of tx d mu is the same as the integral. Since fn converges to f, we can write it like this: fn of tx d mu. And now we can swap the symbol of integral and limit. We're already using the dominated convergence theorem, so we're gonna do it like this. Now, since we already proved it, since this statement is obvious for simple functions, we can use it. Fn of x d mu. And then we can swap the symbols of integral and limit again because of dominated convergence theorem, and we get that f d mu. Okay, so we prove this proposition, which we're going to use a bit later. But right now, let's okay, I'm gonna leave it up there. And now let's prove the main lemma. The lemma that we are going to prove is actually the kind of maximal ergodic inequality type of inequalities. So it's a very powerful one, and our main theorem and Birkhoff's ergodic theorem are gonna follow from this lemma. But proving this lemma is actually going to be quite difficult. We're going to need some work. But before we state the lemma, let me give you some notation. So let fn of x. Okay, so you remember the variables are defined in our main theorem. So in that variables, fn of x will be 1 over n sum from k0 to n minus 1 phi dkx. Fn star are going to be the supremum of fk for k from 1 to n, and f star is going to be just the supremum of fn star. Let's just say by n. And you notice that fn that we defined are quite similar to this part. In fact, this thing is basically an fn. Okay, so now we're ready to state our first lemma, and the most important one. Let's name it lemma 1. So now we have lambda and f are integrable functions on our space X, and let lambda be t invariant, and let lambda be t invariant function. Then the following integral is positive. So this integral is positive, and here I'm using the notation of f star. Well, okay, now let's begin the proof of this lemma. This lemma we're going to prove in 2 steps. The first step is going to be we're first of all going to prove it for L1 for L infinity functions, and then we're gonna generalize it to L1 functions. Okay, so first of all, let's imagine that f is L infinite function. Now let's define a subset En. This En is just consists of points x from our space X, such that fn star of x is greater than lambda of x. Okay. So now what we're going to prove, my claim, which is not so obvious one, is that there exists such an integrable function m, that we have such that for any m we have the following inequality: the sum f minus lambda times characteristic function of En of tk of x is greater, and the sum from k equals 0 to m is greater than our function m of x for any m. Okay, so let's begin the proof of this claim. We're gonna need it. Okay, so let's find the first term. So we have a series, a sum of terms that we need to prove that is greater than something. Okay, so let's find some te of x. Let's find the first te of x such that te of x is in En. Because if te of x, it might be not in En. But if it's not in En, then the term is 0. So it's going to be like 0 plus 0 plus 0 until we find the first one. So let the first one be te of x, such that te of x is in En. But what does it mean that te of x is in En? In fact, it means that fn star of tex is greater than lambda of tex, t to the times ex. But since lambda is a t invariant function, we can get rid of this t and just write lambda of x. Okay, but we also know that fn star is just the supremum of fk's for k less than n. But since we know that the supremum is greater than something, than some fk, then there should exist such j less than n, less or equal than n, such that fj of tex is greater than lambda of x. Okay, but now let's use the definition of fj. It should be written here. We use the definition of fj, and we just write 1 over j sum from k0 to j minus 1 f t e plus k x greater than lambda of x. Okay, but now what we are going to do, so we have this inequality. We're going to multiply both sides by j and use the fact that lambda is t invariant. So we can insert some letters t's in the sum that we're going to have on the right hand and then move it to the left hand side. So we're going to have something like this. Okay, so we're gonna. Okay, so we got this one. So we have this inequality, and now we're also gonna need a quick note that I'm gonna write somewhere here. We're gonna use the fact that f minus lambda times the characteristic function of the set En is greater or equal than the f minus lambda function. Well, it's obvious, because if well, let's put some in some point x. If the point x is in En, then it's equal, obviously. But if x is not in En, then the left-hand side is 0. So the right-hand side should be less than 0. But if x is not in En, then Fn star of x is less or equal than lambda of x. But Fn star is a supremum, and the supremum is less or equal than lambda of x, then any k, then for any k, fk of x should be less or equal than lambda of x, including for k equals to 1. So we can write for k equals to 1, we're going to have so if k equals to 1, then f1 of x is just f of x, and we get that f of x is less or equal than f of x is less than lambda of x. So we get f of x minus lambda of x is less than 0. So we get what we need. On the left hand side we have 0 if x is not in En, and on the right hand side we have something less than 0. Okay. So now we have. So look at what we've got. We have here it's not lambda of x, it's just 0 because we moved it to the left side. So using this inequality and this inequality, we can write. We get the fact that sum from k to e plus l f minus lambda times the characteristic function of En of tkx is greater or equal than sum from k equals e to e plus l f minus lambda out tk of x. Yeah, so we just use this inequality of this inequality, and we get this inequality, and this is also greater than 0 because we've already proved it. Okay. So what have we proved? We have proved that this sum is greater than 0, and if you look closely, it looks really familiar to this sum. To the sum on the right hand side of this inequality. So what I'm gonna do right now is I'm gonna notice that okay, maybe we have some 0 terms in the beginning, then we met the first non-zero term, then there is some j less than n, some less than n terms whose sum is positive. Then there may be another string of zeros in our sum, but then there might be again some positive sum which has less than n terms. So what it means effectively, I'm gonna write it informally like this, is that there exists such j less than n, such that sum from k 0 to j to m minus j is f minus lambda, that function that we've got here, tkx, is greater than 0, is greater or equal to 0. But what this function means, but what this inequality means is that we can add to both sides the last g terms that we haven't written. So we're going to get something like sum for kg to m f minus lambda characteristic function of if en tkx is going to be greater than the last terms that we added to the both sides, m minus j to m, and here is the same thing, the same function, en tkx and so on. Now this one, okay, so let's analyze the last g terms in our sum. It's obviously greater than g times the following thing, because every term is greater than this thing. And here we are using that we live in L infinity space, because this one exists. Greater or equal, and now we can just replace this g with the letter n. Yeah. So we get something that doesn't depend on m, that doesn't depend on m. So we basically found m of x. Now we're just gonna denote this thing as m of x. Okay, so we proved this thing. The thing is the thing. Okay, so it goes up, down. So what we have done is we have proved, I'm going to use it right here, where we've proved this inequality from k equals 0 to m, f minus lambda, okay, so how do we get to the integrals that we need for our lemma? Well, first of all, we're going to integrate both sides. Okay, I'm not going to write. It's an integral of m of x. And then we're going to use the proposition 1 that is maybe already gone, but we use there that we can just get rid of. That if t is a measure preserving transformation, then we get then in the integral we can get rid of it. So using proposition 1, let's write it like this, we can get that the integral of en, and this characteristic function obviously goes to the domain of limit, domain of integration. Let's not forget d mu is going to be greater or equal than 1 over m integral of m d mu. Okay, so what we're going to do now is say the obvious thing, that since m is arbitrary here, we can conclude that en of f minus lambda d mu is greater or equal than 0, because m we have proved this summary equation for any m, so it's got to be greater than 0. But now this inequality is rather similar to the ones that we stated in our lemma. So what we're going to do is just take the limit as n goes to infinity and use the dominated convergence theorem to get exactly what we need. Okay. So it was the first part of the proof. So we've proved our lemma for L infinity functions. Now let's do the last step and prove it for L1 functions. Well, if f is an L1 function, let's look at Gn functions that look like this. They're just f of x times the characteristic function of the set of points in which f is less than n of x for any n. Now the obvious thing to note is that Gn functions are obviously L infinity, so we can use on them our first step, the thing, and also another obvious thing to note is that Gn converges to f almost everywhere, pointwise. So also if we fix n, we get that we can also get that Gn n star converges to almost everywhere to Fn star. It's the obvious statement from the fact that Gn converges to f. And also another thing to note is that the measure of places in which Gn n star n large is greater than some lambda, and Fn star is also greater than some lambda, goes to 0. This is a symmetric difference. Okay, so now what we are going to use is we are going to use our lemma on Gn, since Gn are L infinity functions. We can write it like this, and here we're going to have Gn but this integral, it converges to the integral f minus lambda over Fn star is greater than where Fn star is greater than lambda. We can get it just by getting n to infinity and using again the dominated convergence theorem that is stated right here. And after which, the only thing that left is just to the only thing that left for n large is also to go to infinity, and we get our lemma, our main lemma. That is this one. Okay. So we've proved this inequality with the integral, but how does it connect it to our main theorem? How is it connected? Well, now we're going to quickly. That's what we're going to do next. Is to see how can we get to our main theorem, which is so cool. But before we get to it, let me introduce some notation. Let f upper hat be such limit and f lower, I'm going to call it f lower hat, be this limit. So basically, supremum at infimum of Fn as n goes to infinity. Lemma 2, which is not as scary as lemma 1, is that f upper head and f down lower head are t invariant functions. And the proof is quite straightforward. We're just going to write it like this: f1 fn of t of x is 1 over n sum from k1 to n f of tkx a bit of a trick. We're going to write it like this. So we basically added and subtracted 1 over n times f of x, and this thing is just this thing is just basically fn plus 1 of x. So we get n plus 1 n times fn plus 1 of x is 1 over n f of x. Okay, so we get this equality. So what we're going to do now is we are just going to take limit and supremum of the both sides and get the fact that f upper head equals to f upper head of x. So yeah. And that's it. We've proved our lemma, and the same thing holds for f lower head. Okay. So we have our lemma number 1, and now we have lemma number 2. So we're gonna use both of them to prove our main theorem. Okay, so how do we get from basically this lemma to our main theorem? Well, let's prove this claim. This claim states that integral of f is greater or equal than integral of f upper head d mu. Where again we're going to split our proof into cases. The first case is going to be that f is lower bounded by some real number. So if f is lower bounded by some real number, then we can use such functions phi n of x, where phi n is just the minimum of f upper head of x and minus 1 over n. So a couple of obvious things to notice is just the fact that phi n converges pointwise almost everywhere to f upper head. Phi n are t invariant. This is just lemma 2 that we've already proved, and also that phi n are L1 functions, and phi n are bounded. Okay. Now, since Fn star is just supremum Fk, no, not Fn star. Let's look at F star. Let's look at F star. F star is just a supremum of Fn, which is obviously greater than equal than the limit of the supremum of Fn, where n goes to infinity, which is exactly F upper hat, which is greater than phi k. So we basically know that the points on which F star of x is greater than phi k of x is the whole space. So let's apply our lemma 1 to these phi n functions. What we're going to get is the following thing. So I just applied lemma 1 and the fact that this is our entire space. You can write it, you cannot write it, or you can just not write it. Okay, so what's left to do? And so let's just move k to infinity and use the monotone convergence theorem that is written here. So once we apply that, we get exactly that integral of f is greater or equal than integral of f upper hat, because phi k converge to f upper hat. Okay. So what's left? What's left to prove? So we had this claim. What's left to prove? We suppose that f is bounded below by some real number. Now let's look at the case if f is not bounded below by some number. In this case, we are not going to define functions phi n. Instead, we are going to use functions gn of x, which are going to be defined this way. Yeah, so basically if function f of x goes below n, the gn of x is just going to be minus n. So functions gn are obviously integrable, and they decrease to f. See, since we can just use the first part of the proof of our claim, so the fact that gn is greater or equal than gn hat is greater or equal than minus n times mu of x. But I mean, you can write it, you cannot write it. So now, since gn monotonally converges to f, and gn hat obviously monotonally converges to f upper hat, gn upper hat converges to f upper hat, by monotone convergence theorem we are going to get that integral of f is greater or equal than integral of upper hat. Okay. Okay, so we proved this nice claim. Now there is just only one part left. Just only one step left. I'm going to erase lemma 2 because it's quite obvious and clear. Okay, so we know that. So we already know that integral of f is greater or equal than integral of f upper hat. But now let's apply this statement to minus f. Since minus f upper hat is just minus f lower hat, we're going to get the fact that minus integral of f lower hat is less than equal of minus integral of f. But that means that the integral of f is less or equal than the integral of f lower hat. But hold on, f lower hat has got to be lower than f upper hat. But by our claim, we know that the integral of f is greater than integral of f upper hat. So we get that integral of upper hat is greater than integral of upper hat. So everything in between these two inequalities should be equal. So integral of f minus integral of upper hat, like integral of upper hat minus integral of lower hat, the mu is got to be 0. Well, that means that f is equal to f hat is equal to f tilde almost everywhere. And where f tilde is just the limit of fn where n goes to infinity. Okay. So we proved the first claim of our main theorem. What about the second one? Well, we've already proved by lemma 2 that I raised that f star is t invariant and f upper hat is t invariant. And since f upper hat is t invariant, we know that f is also t invariant. Now the last thing that's left to prove for us is that integral inequality for any t invariant subset of our Borel sigma algebra. To prove it, I'm going to give just a short note for the proof. You should use function h, which is just f times characteristic functions of the set A that we need. So then you can write the following equalities. This is just the first one is just this definition. Is just definitions of fn functions. Here it should be Hn and fn functions. And then we're left only with this. And this equality obviously holds because A is t invariant. So we get that the integral of difference of these two functions is 0. So Hn is almost everywhere equal to characteristic function of A times fn of x. Now we just take n to infinity, and get that h tilde is equal to characteristic function of a times f tilde, and well, obviously almost everywhere. And since h upper hat is equal to h tilde, we can apply the four inequalities to get that integral of f upper hat f h we can apply the four inequalities which are given here and get that integral over t invariant subset of f tilde is really equal to the integral of our function f. Okay, so now we are almost at the end. Now we're almost in the end. So we proved our main theorem. So what's left for us? I can now erase that one. I can now erase our lemma 1 since we won't need it anymore. So you see, so far we haven't used the ergodicity. And the theorem that I'm aiming to prove is called Birkhoff's ergodic theorem. So where does the ergodicity appears here? Well, let's give a quick reminder. Let's look at a quick reminder what ergodicity is. So the t from x to x. So obviously measure preserving function on our space X is ergodic if for any a from our Borel sigma algebra such that a is t invariant, the measure of a is either 0 or 1. Okay, so that's the reminder of ergodicity, but we won't use this definition of ergodicity. We're actually going to use another one, and this is going to be called lemma 3. So t is ergodic if and only if every t invariant integrable function is constant. T invariant. Well, constant almost everywhere. So the proof is going to be a short one. So first of all, let's suppose that we have an ergodic in this sense transformation and t invariant function. So what you need to notice is that for any real number r, the set AR of points of x such that the function f of x is greater than r is obviously measurable, and so it is in our Borel sigma algebra and t invariant. So using this definition, the measure of AR should be either 0 or 1 or mu of x if we have the space x which is not normalized. But this condition is only possible if f is constant, because because otherwise there would exist such Q that which would lie in between these two measures. So there would exist Q such that the measure of AQ is between measure of 0 and the whole measure, which is going to be 1. This is just the definition of constant function, almost. Okay, the other way around is even simpler. So if we have an invariant integrable function, so if every invariant integrable function is constant, so let's suppose that we have some subset E from our Borel sigma algebra, which is invariant, which is T invariant. So the characteristic function of the subset is constant almost everywhere. But that means that the measure of E is either 0 or 1. So in fact we are going to use, later we are going to use not this definition of ergodicity, but this definition of ergodicity. Okay, so что стереть. Okay, let's erase this thing. So finally, we are ready to state the Birkhoff's ergodic theorem and the proof. And this we've already done all this job, all this work. The proof of Birkhoff's ergodic theorem is going to be quite simple. But first of all, let's state that T is ergodic, right? Birkhoff So what the theorem says is that if T is ergodic, if and only if for any integrable function f, and almost every point, almost any point x from x, the other function f tilde, which is defined right over there, then I'm going to rewrite the definition. So this function not only exists, but it is also equal to 1 over mu of x times integral of f d mu. So basically, what this theorem means is that time, so the letter T for our measure preserving transformation is not coincidental. It's the short abbreviation for the word time. So what the theorem says is that if our transformation T is ergodic, the time averages, which are on the left-hand side of our equality, are equal to the average, to the space average of our space. So the proof shouldn't be long. Now let's assume that T is ergodic. So we need to prove this equality, right? So we already know that f tilde is T invariant. So f tilde is constant almost everywhere. And moreover, f tilde is constant almost everywhere because of the definition of ergodicity that we're using right now. The integral of f d mu should be the integral of f tilde d mu. But since f tilde is constant, we can write it like this. It's just f tilde times mu of x. So let's integrate over our space x. So now we just find from these two equalities, we can just write that f tilde of x is just 1 over mu of x times the integral of x phi f d mu. All equalities in this theorem are unfortunately almost everywhere. And okay, now the only thing that I have to prove and is from the other side, if this equality holds, then T is ergodic. Now assume that for any f tilde is constant almost everywhere. Okay, let's just write f tilde of x. Let's just write the definition of it first of all. There should be n large and well, if f is t invariant function, then this limit is just equal to f of x. So f of x is constant almost everywhere, just because f tilde is constant almost everywhere. But that means that T is ergodic by our definition of ergodicity. And that finishes the proof of Birkhoff's ergodic theorem.